Hey, thanks for having me. It's my great pleasure to be here. I'm Taysun Kimm from Yonsei University, and today I'd like to talk about Lyman alpha emission from galaxies, and how we can use this information to better understand the galaxy formation. And I guess this is probably a very distant topic that we've been discussing today, but I think that we have some common interest in the sense that the co-evolution of the cosmic web and galaxies, and potentially its interpretation, requires a bit of understanding how galaxies form and evolve. So in the next 20 minutes or so, I will start with a rather brief introduction about what is the current issues in galaxy formation, and how the Lyman alpha, why Lyman alpha information is interesting and useful, and then discuss what we can learn from this comparison between simulations and observations. And hopefully I will give some football thoughts. Okay, so as you are well aware, recent hydrodynamic simulations such as Horizon AGN, Eagle, Galaxies enjoyed a lot of success in reproducing the bulk properties of galaxies, but detailed predictions differ, and different simulations were sort of required to use their own calibrated feedback models. But this was kind of unavoidable because the resolution was finite, and the physical processes that are responsible for the evolution of galaxies were not fully resolved. But with the zoom-in techniques, we are now beginning to resolve quite a bit of physics in the simulations. And this is one example we have done a couple of several years ago with probably low resolution than the latest simulations you might have heard before. This is a Redshift 753. This is a galaxy at 10 to the 11th solar mass dark matter halo at Redshift 3. And you can see that there is a very extended, a very nice prominent cold flows with developed supernova bubbles. And what we found is that despite the larger number of supernova explosions there, we always find basically that too many stars form and galaxies were too compact. And this is something called overcooling problem. And we've been trying to really tackle this issue for many, many years. And so several ideas were proposed. So I listed 4 of them. The first one is a superbubble feedback, and this is about how we have to model the spatial distribution of supernova. And this is probably something to do with the star formation as well. And some groups say that we need to do something about the supernova momentum, because we are not understanding the physics fully. And of course, the radiation from young stars is known to operate very early and suppress the star formation. But since it operates so early, they tend to suppress the clustering of supernova, sometimes making these outflows weaker. And non-thermal pressure from cosmic ray is also known to control the star formation while driving gentle winds. And I won't be able to tell in this talk which model is more realistic in this talk. Rather, I'd like to emphasize that different models tend to predict different temperature distributions. So here, I just took it from Marion Foss's paper here. So this is the model with a different galaxy mass, and you see that the simulations with the supernova feedback tend to predict a very hot CGM, whereas if you have a cosmic ray, then you have a very warm CGM. And I think that these differences are likely to leave some imprints in observables that are very sensitive to gas kinematics. And I believe the Lyman alpha is a perfect tool, probably a perfect tool to study this. So I prepared a couple of slides just in case you're not familiar with it. And Charlotte gave a very nice introduction this morning. So this is a typical the Lyman bright galaxy spectrum, and you see a very prominent line here, which is a lot. So Lyman alpha is a kind of a special because it's a very bright, easy to observe. And this Lyman alpha is produced via 2 different channels. One is a recombination, the other is a collision radiation, and both channels require the free electron with the neutral hydrogen at some point. So that means that these processes are very efficient around 10,000 Kelvinish. So this Lyman alpha is very strong usually around the star forming region where we have a photonization heating. Not only that, if we look at the local starburst galaxy, this is Macquarian 259, we see that there is a Lyman alpha that is very extended compared to this green line. Green color is the far UV spectrum, so that's essentially the stellar component. And this is not the only object. Here on the right, this is the size distributions of galaxies between redshift 3 to 6. These are mostly the Lyman alpha emitters. And the size of the Lyman alpha is factor of 5 to 10 times larger than the UV continuum. So that means that there are extended area with the gas around 10,000 Kelvinish. So of course there could be some neutral medium hanging around, and Lyman alpha coming from the central region, and they will scatter off the light there. So no matter what kind of the mechanisms are responsible for this Lyman alpha halo, we think that there should be some level of neutral hydrogen there in the CGN. And I think that this is very important because Lyman alpha is a radial line. It's very sensitive to the presence of the neutral hydrogen. So here, the typical optical depths we can think of from the galactic environment is like 10 to the 7 or even larger. And that means that every time it scatters, so this is one example of how the Lyman alpha start from here and then diffuse in space. And if that happens, then it diffuse not only in space, but also in frequency. So they form this characteristic double peak profile. And depending on the optical depth, if the optical depth is small, then the separation of the double peak is small. If optical depth is large, then the separation is large. So the separation of the double peak is a measure of the optical depth to neutral hydrogen. And if we compare this quantity against F900, so here F900 is the escape fraction at 900 angstrom, so that is ionizing radiation. And so this is also a measure of the optical depth to H1. But it's slightly different in the sense that it's more sensitive to the high column density, whereas the Lyman alpha is sensitive from something like a 10 to the 14 in column density. So it's not surprising if you look at this galactic observation to show this negative correlation, because you would expect fewer Lyman continuum photons to escape from the medium if the optical depth is large, and if you'd expect the larger separation if the optical depth is large. But what's interesting is that this sequence is obviously different from the case where we assume the uniform density. So there must be something going on here, right? This is one plot that I'm going to use in this talk. And another interesting point of the Lyman alpha is that if you have this double peak, then you can use this flux ratio, blue part or red part of the spectrum, as a measure of gas kinematics. So here, I'm showing you one example taken from Borham et al. And if the gas is static, the characteristic is double peak, the relative ratio, the flux ratio becomes close to 1. Whereas if the gas is expanding, then the red peak dominates and the blue peak, becomes smaller. Likewise, if the gas is falling, then the blue peak dominates. So this flux ratio is a measure of the gas kinematics. So now, if we plot up all the galactic observations here, except for a few cases up there, the flux ratio is less than 0.5. These are basically the star-forming galaxies. I would say this is a rather small galaxies with a stellar mass of 10 to the 9-ish. And the central value is probably around 0.2 to 0.3. And what's plotted on the x-axis is the location of the red peak. So that is the location of the red peak here. And this is again the measure of the optical depth. And the question is whether the simulations can reproduce this, and whether we can learn something about the galaxy formation from these measurements. So what we need to do is to simulate this the Lyman alpha from the star-forming sites to the ISM and even the CGM. And this is because the Lyman alpha is produced by the absorption of the Lyman continuum radiation in most cases. But unfortunately, as you can imagine, simulating these scales from the GMC to the CGM is very challenging. So we're going to just look at these three different scales individually. So here I'm showing you one example of the evolution of the GMC. So you see the stars forming here, and once the photonization heating blows everything away, then heats up and blows away within a factor something like a 5 megayear or so. It's a very efficient process, and we have run these simulations for different morphologies, surface density, and various diverse conditions to see whether the Lyman continuum profiles are formed inside the GMC or outside the GMC. So we process the data with the Monte Carlo Lyman alpha transfer code called ROXCAS. And initially, when the gas is, the stars are just few stars are formed, then you can see that the majority of the Lyman alpha photons are just get destroyed. And the Lyman alpha is brightest when the GMC is being destroyed. And at this time, the separation is on the order of 100 kilometers per second or so. And once the gas is completely dispersed, then you no longer have the neutral hydrogen that can convert the Lyman continuum to Lyman alpha. So the Lyman alpha profile becomes very faint. And what about these two diagrams, separation and the flux ratio? And you see that these are, again, the Galaxy observations, and the simulations are all down here. So initially, it was its diffraction was very low with a large separation, and it goes like this. So that is the evolutionary sequence. And what we found is that compared to these Galaxy observations, these GMC simulations take up very different space. And this is more close to the uniform case with potentially with a little bit of the velocity dispersion. And on the right-hand side, because the location of the red peak is essentially half of the separation, it's just clustered around 50 kilometers per second, which is very, very small. And the flux ratio is again clustered around something like a 0.5-ish, which is again rather large compared to these Galaxy observations. So that's kind of in a way, you may say you may find it a bit disappointing, but I think it's very promising because we can now use the larger scale simulations to see whether the Lyman alpha we see in observations can be used to understand the the ISM and the CGM kinematics. So now we use the isolated disk simulation. We ran 5 different simulations, but I'm going to just focus on this one, which is the low metallicity with the large gas fraction. So the gas to stellar mass ratio is 5. Okay, and you see it's pretty puffed up, and it's sort of I think this is quite similar to what we think as a high redshift galaxy, high redshift star-forming galaxy. And we measured the Lyman alpha luminosity and the UV continuum magnitude and compared with the existing data, and they seem to lie in the more or less the same area. So that's a good start. And by the way, the stellar mass is 10 to the 9, so this is kind of chosen to have more or less the same mass range as observed. Now, what about the separation? So here, these data points are the simulation with from the gas bridge configuration, and you see that now the separation becomes very large. Okay, that is very good news, I think. But if you look at the flux ratio, these data points here, blue one, they are clustered around 0.5. So we're not really getting there down there. And what is more interesting to me here is that we are missing largely this data point. I mean, we can't really recover this data. So this is interesting. So these are galaxies with a low flux ratio, with a large red peak location. So that if we want to reproduce those guys, we need outflows, neutral outflows that are thick enough to give the low flux ratio and the large separation. So at this point, you might wonder, okay, what happens if we have the cosmic inflows? So Jeremy Blyser recently submitted a paper. This is a cosmological simulation now. This is just one galaxy, and I have just a limited number of samples because it's very difficult, very expensive to run. This is a galaxy in a 5 times 10 to the 11th 10 solar mass, and the galaxy stellar mass is still 10 to the 9 at redshift 3. And this is 2 different epochs, and the color codes indicate the inflow, and this is outflow. And this is so this is a rather inflow dominated in terms of the covering fraction, and this is outflow dominated. What is interesting here is that if you look at the inset of the diagram, which is the Lyman alpha profile, they are red peak dominated. So like I said, if the spectrum is red peak dominated, it's indicative of the outflows. Okay, and what you can see here is that even though you have a large covering fraction of inflow, your signals are still dominated by the outflow. It's more sensitive to the outflow, and that is very good news because we can use Lyman alpha to study the outflowing features. And this is, I think, this is a lot of achievement in the sense that Peter Mitchell with Jeremy Blyser did the same simulation, exactly with the same initial condition, but did the same simulation with a weaker supernova feedback. And what they found is that instead of the red peak, it was the blue peak that dominates the spectrum. So it was more inflowing rather than outflowing. And I have to say that we have cranked up the feedback here by a factor of 4 to make it work. But you can see that the spectrum is red peak dominated. This means that we need very strong outflow to reproduce the Lyman alpha. The question is, before we get to the point, so we also look at where these Lyman alpha lines are formed. So we we measure the Lyman alpha profile at the, so this is measured at the 0.2 video radius, and this is measured at the 3 video radius, and we term after ISM or after CGM. Yep. And you can see that, what you can see here is that the presence of the CGM tends to suppress the blue peak. Okay, so that gives you the low flux ratio, and the CGM acts like a screen to Lyman alpha, and that's good news because we can use the CGM. Lyman alpha is reflecting the gas kinematics very efficiently. But here, if you look at the red peak location, no matter what the CGM, well, regardless of their CGM, their peak locations are more or less the same. So if I were to plot the flux ratio against the red peak location, the data that I showed earlier are populated somewhere here. Okay, so we are still missing quite a bit of data. Well, we can't reproduce these data still. There could be multiple interpretations why we are not reproducing those galaxies with a large red peak. One interpretation would be that, okay, we have just one galaxy, so we need more simulations to see how the bursty star formation occurs and affect the flux ratio. Or another interpretation is that we need a neutral outflow somehow. And as I explained earlier in the introduction, this could be one possible way is by having cosmic rays, and this is something that we should work on the next couple of years. So I'm going to skip this case part. So just to summarize, I hope I convinced you that the Lyman alpha from GMC is not just wide enough to explain what's observed in galaxy scales, which means that we need more components, and the Lyman alpha itself is more sensitive to the ISM and the CGM. And hopefully with the neutral outflows, then we should be able to better explain the what is observed. But this requires a bit of simulations that will take a lot of time, CPU time. So I'm hoping to report some new results in the near future. Thank you.
Thank you, Taysun. Questions?
It's more clarification than a question. Did you say that if you weaken the supernova feedback, you get a poorer match or a better match?
It's a poorer match because the flux ratio is now over 1.
So your work suggests one needs strong supernova feedback.
Yeah, so we need a stronger supernova feedback, but it doesn't explain the large. It doesn't explain the large, galaxies with a large red peak. So we still need a strong feedback of some form, but it has to cover a wide solid angle to reproduce this.
Okay, thank you.
And at the same time, it has to be neutral.
Thanks for the talk. So I have questions about the fact that you missed your strong neutral flow as the answer. So you said that one possibility could be due to the fact that you didn't simulate the right objects, right? Or you don't have enough objects. So I have two questions. So how did you choose the object to run your experiment, the kind of galaxy to run your experiments, and do you already have an idea of what should be the type of objects that you need to simulate in order to reproduce this trend?
Okay, so initial conditions are very difficult to pick up. So, and I think Jeremy Belanger tried to pick up one of the halos that maybe there could be a sample of the Lyman alpha emitters. Okay, the halo mass is close to 10 to the 11 solar mass, and that's the typical dark matter halo mass we can think of for the Lyman alpha emitter. And regarding this sample, we need more sample in the sense that this is one galaxy, and we're not quite sure whether there could be. I mean, there could be some objects with a very intense starburst, and perhaps they could explain those. But I think it will. I mean, it depends on how many galaxies we have, and obviously the number of data we have is quite limited at the moment. So.
Yeah, so I have a comment about the, so you say that you need some neutral or, warm ionized phase, extra phase in the CGM. So in all these cosmological simulations where we do quasi-Lagrangian refinement, the resolution in the CGM is very poor. As soon as you're out of the galaxy, the resolution drops. So how much do you think, you would gain by, in terms of phase mix or multi-phase CGM you would gain by increasing the resolution of the simulations? Have you checked that just in the CGM?
Yeah, so that's a legitimate concern, and I think that of course we will have to run the simulation to make sure that that's actually the case. But my impression is that if you increase the resolution, then it will form. There will be some instability and form the neutral hydrogen, but it's that they tend to be rather clumpy, and if that is the case, then it's not going to affect the Lyman alpha profile. Like I said, even when there is a cold flow like this, the Lyman alpha features are still dominated by affected by the outflows, because Lyman alpha tend to scatter along the low density channels.
Okay, so you want to diffuse warm ionized CGM.
Yeah. So it's going to be great if you have a neutral diffuse CGM that is slightly expanding.
Cosmic rays now.
Yeah.
Other questions? Online.
Yes. This is Michael Rausch. I have a question. It used to be the case that Lyman alpha profiles were well modeled by expanding shells. This means that the spectrum was always well modeled, but the surface brightness profile of expanding shells were never seen in observations, which led some people to suggest that these must be really very small-scale outflows. Is this something that's consistent with your models?
That's a very good point. We haven't checked the surface brightness yet, but that is still one of the projects we will have to work on. So Jeremy is working on it right now, I think. And one thing I'd like to comment on is that in the Peter Mitchell's paper, they argue that they reproduce the surface brightness with from this cosmological simulation. So I think that I mean, we will have to process it. I can't really say for sure at this moment.
Thank you.
Yeah, I was wondering if you could just clarify the statement that you were making about requiring a large covering fraction of the outflows. Mm-hmm. I was just looking at this again because, I mean, here it seemed like you were saying that the outflows will always dominate over inflows. And so you'll always, I mean, you always end up with a red peak and then the CGM will just, or the IGM will just kill the blue peak. So to me, it seems like it doesn't, you just need to have like one really strong outflow, and then you can get loads of Lyman alpha photons out at high velocities. Or is that not the picture that you have?
Yeah, that's a very good point. So I think what I mean by here is that, if you have a low density channels, then this Lyman alpha will just, leak out along these low density channels. So what I mean by we need to have a larger, stronger outflow is not just having the outflow. We need the outflow with a large covering fraction so that they don't just escape through low density channels. And that's why, so for instance, here you see this outflow here, and we want this to be more covering and at the same time neutral, so that we can explain the largest separation. Does that answer to your question?
We can talk about it afterwards.
Okay, maybe we can take one more question while the next speaker comes forward. No other questions? Not online? Okay, well then let's move on to the next speaker. Thanks, Taysun.